Now we're going to see Lagrange's theorem. Okay, we can start with one example. If h equal to 5z, let us consider h equal to 5z. Z is a set of all integers, and we're going to take the subset h. Okay, then h plus is a subgroup of z plus. Z plus is a group under the operation plus. Okay, so this is a subgroup and that is defined in the form of h equal to 5z. Now we're going to consider the left coset of this. Now if you consider h equal to 5z means h is nothing but it is going to be set of all integers z is. Okay, so 0, 1, 2, 3. In the other side minus 1, minus 2, minus 3 you have. So 0 into 5, it's going to be 0. Next one 5, 10. It goes on. Okay, fine. The other side it is going to be minus 1. Z is having minus 1. Minus 1 into 5, minus 5, minus 10. It goes on. Okay, this is h. Okay, now we can consider the left cosets. Okay, left cosets of this. So order of 0 plus h. Okay, left coset is nothing but first we consider 0 plus h, which is equivalent to what we'll get if you add 0 with all these elements. You're going to have that same element. So that is going to be minus 10, minus 5, 0, 5, 10 up to etc. Now if you consider 1 plus h, left coset of 1 plus h, that is going to be is nothing but it's equivalent to 1. You will get 6, 11 up to etc. This is going to be minus 4, minus 9 up to etc. on the other side. 2 plus h, what you will get? 2 plus h is equivalent to, you will get h plus 2. So that is 2, okay, 7, 12 up to etc. And this side it's going to be minus 3, minus 8, it goes on up to etc. 3 plus h, what will get? 3 plus h is nothing but it's equivalent to, add 3 with h, okay, so that is 3, okay, 8, 13 up to etc. And other side it's going to be what? Minus 2, minus 7 up to etc. 4 plus h, okay, 4 plus h is nothing but 4 plus h is, if you add 4 with this now, you will get 4. This is going to be 9, this is going to be 14 up to etc. On the other side it is going to be minus 1, right? 4 minus 5 minus 1, 4 minus 10 minus 6 up to etc. Now you have the sets. Okay, now once again I'll go for 5 plus h. 5 plus h is nothing but it is going to be, okay, 0 plus 5, it's going to be 5, okay, next it's going to be 10, next 15 up to etc. And this side it's going to be 5 plus minus 5, it's going to be 0, and then it's going to be minus 5, 5 minus 10 is minus 5, it goes on. This two set is equal, is that right? This both are equal, okay, equal. Now if you consider 6 plus h, it's nothing but 6 plus 0, it's going to be what we'll get? 6, okay. 6 plus 5, 11, okay. Next 6 plus 10, 16, it goes on. On the other side, 6 plus minus 5, it's going to be 1. 6 plus minus 10, it's going to be minus 4, up to etc. So this and this sets are going to be equal. So if you keep on tracking this, okay, 7 plus h, 8 plus h, 7 plus h is going to be equal to, this is equivalent to 7 plus h, this is equivalent to 8 plus h, okay, this is equivalent to 9 plus h. Once again 10 plus h is equivalent to 0 plus h, okay. This is what you're going to have. So the left cosets are like this. So what we have, consider this here, this is a H, okay, this is a Z, okay, this is a Z. Now we have all the partitions, okay, for we can take looks. This is partitioned into like this, okay, this is 0 plus H, 1 plus H, 2 plus H, 3 plus H, and then finally 4 plus H, okay. If you add all this, okay, all this partitions, okay, this all called the partitions, okay, if you add all these partitions, 0 plus H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, if you take union of all this, it is nothing but it's going to be Z, okay. This is what we're going to see in the first theorem, okay, partition theorem, it's called the partition theorem, okay. This is what we're going to see there in the partition, okay. The first theorem, what is the inference we got from here, okay, if you take two left cosets, either it is going to be equal, okay, if you take two left cosets, consider two left cosets that might be equal, okay, for example, this 0 plus is equal to 5 plus h as well as 10 plus h, 15 plus h, it goes on, okay. If you consider any two left coset that might be equal or intersection of different cosets, so for example 0 plus h, 1 plus h, what is the intersection? There is no common point between these two, okay, the intersection is going to be empty. For example, 0 plus h intersection 1 plus h, what is the intersection? That means empty, okay, it is equivalent to empty, okay. That is what the first inference we got, okay. Next one, suppose if you take 0 plus h must be equivalent to what is 5 plus h, okay, this is nothing but 5 plus h. So either the intersection of two left cosets is equivalent to empty, or it's going to be equal, okay, or it's going to be equal. That's what we have, okay. Now we're going to see, okay, this is what equal, okay. Now let us consider the theorem, first theorem, okay. So what's the theorem going to say, okay, theorem, the order of, we're going to see Lagrange's theorem. Before seeing the Lagrange's theorem, we need to know other three theorems, okay. So first I will write that theorem, the order of, that is Lagrange's theorem. First we go for the partition theorem. Let H star be a subgroup, H star be a subgroup of G star, then the set of all left cosets of H in G form a partition of G, that is every element of G belongs to only one left coset. Only one left coset of H in G. Okay, this is what the first theorem we're going to prove. Okay. Now, what does that? H star be a subgroup of G star, then the set of all left coset of H in G forms a partition of G. That is, every element of G belongs to only one left coset of H and G. That's what we have shown here. Okay, so in this example you can see that H star is a subgroup of G star, but we have taken here example Z and H. Okay, and then the set of all left coset of H and G forms the partition of G. This is the partitions. The first four partitions is 0 plus H, 1 plus H, 2 plus H, 3 plus H, and 4 plus H. This will form the partition for Z. Okay, then that is, every element of G belongs to only one. Yes, you can see this first four sets you can take it. Okay, first five we can take this one. Every element of Z this belongs to any one of the left coset. Every element of Z will belongs to only one left coset. Okay, so that is what we're going to prove here. So already we have taken the inference of this. Okay, using this only we're going to prove. Okay, let's go for the proof. Okay, let us consider, we have to consider two left cosets. Let AH and BH be the two left coset. Be any two left coset. Any two left coset. Left cosets. Okay, be any two left coset. Now we have to prove that either it's going to be equal. Okay, I already told, either it is going to be equal or their intersection is going to be empty. Okay, so this two left coset should be equal or it's going to be empty. Okay, we shall prove that. We shall prove. Okay, either AH equals to BH or AH intersection BH equal to empty. We can prove that either it is going to be equal or AH intersection BH, different to left coset intersection, is going to be empty. Okay, fine. Now suppose we have take for the negation part. Okay, suppose this is not true. Okay, let us consider this is not true. Okay, AH intersection BH is not empty. AH intersection BH is not equal to empty. That means these two sets might have a common element between them. 0 plus H and 1 plus H. That's what here we are saying. AH intersection BH is not equal to empty. Okay, that means there is a common element between for any two sets for this two. Okay, let I consider in general X belongs to AH intersection BH. Okay, if this is not equal to empty, so you can write X belongs to AH intersection BH. Okay, then that X will belongs to, okay, that X belongs to AH. If it is belongs to intersection, definitely it will belongs to AH as well as BH. Okay, and X will belongs to BH. Okay, X will belongs to BH. Fine. Now the left coset form is going to be nothing but X equal to, we can write that in the form of A star A star H1. Okay, A star H1. And this is going to be different left cosets. That is going to be X equal to B star. You can take any other element H2. Okay, two left coset. X equal to A star H1. X equal to B star H2. I am taking two. This electron X element is going to be B star H2 and E is going to be star. This both are equal, no? So that is, see, X equal to this one and X equal to this one. So I can write this as, I will write here, A star H1 is equivalent to B star H2. Okay, A star H1 equal to B star H2. Now you can post multiply by H inverse on both sides, H1 inverse on both sides. Since H is a subgroup, so it have a inverse also. So A star H1 inverse is equivalent to B star H2 star H1 inverse. Okay, this is going to be identity. Identity into anything is going to be A only. A equal to B star H2 star H1 inverse. Okay, this is what we have. Okay, let us keep this one. Okay, this is, we can keep this one as it is. If, okay, we can consider this if X is an element in H. Okay, if X is any element, in AH, X is any element in AH, so X equal to A star H. Okay, if you take any element in X, then X is equal to what? A star H, and X equivalents to B. This is going to be, we already know that A is going to be this value, so X equal to B star H2 star H1 inverse. Okay, fine, into star H. Okay, because already we know that A is this one. Okay, then this is equivalent to B star H2 star H1 inverse star H. Okay, fine. So this is equivalent to B star. Okay, this value is nothing but this all. Okay, it's going to be in H only. Okay, all this value is going to be in H only. So that can be written in the form of, or I can write this all entire value is going to be in H only. Okay. So this will belongs to BH. Okay, we started X in AH, but we proved X belongs to BH. Okay, that means what you conclude, we started with X belongs to AH, which implies we proved that X belongs to BH. Okay, that is, this is going to be subset of this. Okay, so you can say AH is subset of BH. AH is subset of BH. Similarly, I will write here. Similarly, we can prove. Similarly, we shall prove. We can prove BH is the subset of AH. Okay, this is 1, this is 2. Similarly, we can, in the same step, if you take any element y belongs to AH and y equal to B star H. Okay, so similarly start from the beginning and you can prove that. Okay, fine. So that is possible. So similarly, we can prove BH is subset of AH from 1 and 2. If AH is subset of BH and BH is a subset of AH, then you can able to write, you can say AH equal to, this is possible only AH is equal to BH. Okay. This is possible only AH equal to BH. Okay, so that is what, see here, we have started with it is not empty. We started with it is not empty, but finally we obtained here AH is equal to BH. If it is not empty, okay, intersection is not empty, then definitely it is going to be equal. That's what I have said here. Okay, so this, if either it is going to be disjoint, two left coset, if you take intersection for that, that is going to be disjoint, or that two states are equal. If it is not disjoint, that is going to be equal. That's what we have proved. We have started with the disjoint. Suppose we consider the contradiction, that is not disjoint, that is not equal. Okay, these two are not equal, so there is a common element, but we prove that if it is not equal means that both are going to be equal. Okay, that's it. Okay, that is what we have proved here. Okay, now we go for in this extension into the general form. Okay, so thus we take thus any two left coset. From this we can conclude thus any two left cosets are either equal or disjoint. Either equal or disjoint. Okay, any two left cosets are either equal or disjoint. Further, we extend for the general form. Okay, for nth term. Okay, so union of all the left coset is nothing but Z in the example. So here we are going to take union of all the left cosets. A belongs to G and AH is subset of G. Okay, since union of subsets is a subset, now we are going to take if X belongs to G. Okay, we are taking X belongs to G. if you take x belongs to G means x is going to be what we can able to write x is going to be any element. So there is an identity x equal to x star e we can able to write. So this will belongs to EH, okay, or XH, okay, this will belongs to XH, okay, fine. So x is in a left coset and hence x is in a left coset and hence x will belongs to u union of this x is going to be in one left coset, so definitely it will belongs to union of all the left cosets of AH, okay. So x belongs to G implies x belongs to union of A belongs to G AH. So where we started, x belongs to G we started, okay, finally we prove that x belongs to union of all. So then you can say G is the subset of union of A belongs to G AH. But this is 4, okay, this you can keep as 3. So 3 and 4, what you conclude, this is subset of this and this is subset of this. This is only possible that G is equivalent to union of A belongs to G AH. Okay, so this that is all the left cosets partition of G. All the left cosets is partition G. Okay, that's it. This is the first theorem we have proved. Okay, now we have to go for the next theorem. Okay, now we go for the next theorem. From the example I will explain. I will erase this all. Okay, next theorem what we're going to prove. See this in the example. You can consider this. Okay, for example, you can take this. Okay, one mapping. Okay, this is a mapping. So here you have this is for example order of 0 plus h, and this is going to be 1 plus h function we defined. So here if it is going to be what 0, okay, 5, okay, 10, okay, minus 50, minus 5, okay, and then it's going to be minus 10. So if you add with 1, this will map on to minus 9, okay, this will map on to minus 4. Add with 1, that is going to be map on to 1, this is going to be 6, this is going to be 11. Okay, so what we trying to prove in the next theorem, there is a one-to-one correspondence. Why we need to prove one-to-one correspondence? Any sets you can take, so you can prove that there is a one-to-one correspondence. Okay, any set you can take, there is a one-to-one correspondence. Okay, so why we have to prove that one-to-one correspondence? Number of element of this, okay, order of h, and number of element of this, it's going to be equal. Okay, so that's what we're trying to prove here. So we have to prove one-to-one correspondence, that is bijective mapping here. So how to prove one-to-one correspondence? So one-to-one correspondence means first we have to prove one-to-one, and next we have to prove onto. If you say a function is one-to-one and as well as onto, then it is in one-to-one correspondence. So how can you prove one-to-one? Means you can take two elements in the codomain. Okay, that if you say that is two are equal, for example, this is f of a, this is a means this is f of a, this is b means this is f of b. Okay, if you say f of a equivalent to f of b, then a equal to b. Okay, if you prove that, then you can say it is a one-to-one. Okay, one-to-one. Now we're going to start with this. Okay, for our aim is to prove, okay, order of all the left cosets having the same number of elements. That's what we're trying to prove. Okay, so theorem there is one-to-one correspondence between any two left cosets left cosets of H in G. Proof: let H comma star be a subgroup of G comma star. Let, we are considering H star be the subgroup of G star. Okay, let, we are considering a left coset AH be any left cosets of H in G. We know H itself is a left coset. We know H itself is a left coset. We know H itself is a left coset. So it is enough to prove there is a one-to-one correspondence between H and AH. There is one-to-one correspondence between H and AH. There is a one-to-one correspondence H and AH. Let F is a mapping from H to AH be defined. Let us consider the mapping. Okay, H to AH. So here I am taking 0 plus H to 1 plus H. Here you have to take H to AH. Be defined by F of H equal to A star H for all H belongs to capital H. Okay. We define this mapping as F of A star H for all H belongs to capital H. Okay, fine. Now we need to prove it is a one-to-one. To prove one-to-one. Okay. So how are we going to prove this mapping is one-to-one? Already I told that we take two elements in this codomain, then we have to show that is equal in the domain also. Okay, so that's for any we can take H1 comma H2 belongs to capital H. Okay, so if in codomain it is going to be what? F of H1 is equivalent to F of H2. So this is nothing but left coset. Okay, so that is going to be A star H1 is equal to this, going to be in the form of A star H2. Okay, by cancellation law you can remove that A, so you can write H1 equal to H2 by cancellation law. Okay, so you can write H1 equal to H2. So it is one-to-one correspondence. That's what we have to prove. That is one-to-one correspondent. Now to prove onto. Okay, to prove F is onto. Okay, so what you have to do? There is an element you have to take in the codomain, and there is a mapping. Okay, from codomain there is an image. Okay, pre-image in the function. Okay, that's what we have to prove. Let consider X belongs to AH. Codomain we are taking one element. Okay, X belongs to AH. Be any element. Okay, then we know that here in the form is going to be A star H. For example, 0 plus 1. Okay, so that is what here we are going to have. This H is X is nothing but then X equal to A star H. Okay, then X equal to A star H for some H belongs to capital H. Okay, some H belongs to capital H. For this we have F of H equal to the mapping. Okay, A star H. Every H have a mapping here, that is A star H. So F of H equal to A star H. Okay, that is equivalent to X. Okay, so F is a mapping. Okay, F is onto. So F is onto. Hence, what you conclude? F is a bijective function or one-to-one correspondence. Okay, therefore F is one-to-one correspondence between H and therefore F is one-to-one correspondence between H and AH. So what you trying to conclude here, the number of element in 0 plus H is equivalent to 1 plus H as well as 2 plus H, 3 plus H and 4 plus H from the given example. Okay, so every left coset, what we trying to show here, every left cosets having the same number of elements. Okay, that's what this theorem says. Okay, every left cosets have same number of elements. Okay, next we go for next theorem. That's what the main theorem of Lagranges. This two theorems we're going to apply in the main theorem. Okay, so Lagranges theorem. Okay, this now only it comes. Okay, this above two theorems we're going to apply the Lagranges theorem. Order of a subgroup H of a finite subgroup G divides the order of group, that is order of H divides order of G. So let us consider a group. Okay, let G star be a group of order n. Okay, and H star is a subgroup of order m. Okay, since what we have to prove, order of H will divides order of G. Okay, that's what we have to prove. So we are considering the group and a subgroup with order n. The group is having order m and the subgroup is having order m. Okay, since G is a finite group, this we defined G is a finite group. Okay, G is a finite group. The number of left coset in G is also finite. Okay, so here we are considering, okay, definitely the number of left cosets is going to be finite. It's not going to be infinite, but here example we have taken in general form of all infinite number of elements, but here we are defining a G is a finite group. So what is that you're going to have? Left coset is also going to be a finite one. Okay, fine. That finite means let R be the number of left cosets. There are R number of left cosets of H and G. Let R let the R cosets be A1H. That named be that A1H is one left coset, A2H up to etc. ARH. There are R left cosets. Now union of all this nothing but it's G. Okay, union of this 5 left cosets is going to be Z. Similarly, union of that R left cosets is going to be nothing but it's a G. Okay, fine. It's G. Now we take order of G. Okay, order of G is equivalent to order of A1H union H1 union A2H2 union up to etc. union ARHR. Okay, fine. This is equal to, if you take the order is denoting the elements, number of elements, so it will become addition. So union will become addition. Order of A1H1 addition, order of A2H2, okay, addition up to etc. addition, order of ARHR. Okay, fine. Now this is equivalence to, okay, we already we have seen that number of elements into one-to-one correspondence. In the previous theorem we have seen number of elements of this left coset, all the left cosets are equal. Okay, number of elements of all the left cosets are equal by seeing the one-to-one correspondence. Okay, so I can denote this as, okay, what is that? I can write all are going to be same, so number of element, so I can write order of AI of H is equal to order of H. Okay, because all is going to be same number of elements only. So that's what we're going to apply here. So that is going to be order of H plus order of H plus up to etc. order of H. Okay. So how many left cosets are there? We are considering R left cosets. So 1, 2, 3 up to R. Okay, R will be there, R times. Okay, so that is going to be R left cosets are there. So R, okay, of order of H. Okay, fine. So this is order of G. Now you can see there. Okay, order of G equivalents to order of G equivalents to this, which implies order of G divided by order of H is equivalent to R. That is, R is an integer. Okay, R is an integer. So order of H divides order of G. Okay, therefore order of H divides order of G. This is what Lagrange's theorem. Okay, this is what Lagrange's theorem.